Today we are looking at a paper titled ICALens, Interpreting Language Models Without Training Another Dictionary by Sita Liu and Feijiang Han. Imagine spending 20% of a supercomputer's total power just to build a dictionary that translates what an artificial intelligence is thinking.
Which is wild, right?
It is, because in the quest for mechanistic interpretability, sparse autoencoders, or SAEs, have become the absolute gold standard for finding these interpretable features inside neural networks. But here's the problem. They are brutally expensive to train and store.
Oh, absolutely.
So this paper asks a radical question. What if you don't need to train a new neural dictionary at all? By reviving a classical statistical method from the 1990s, independent component analysis, or ICA, the authors prove that highly interpretable non-Gaussian feature directions already exist right there in the activation geometry of the model.
Just hiding in plain sight.
Exactly. The authors introduce ICALens, which is a pipeline that makes ICA stable on modern LLMs like GPT-2, Gemma 2, and Qwen 3.5. And they prove that ICA is highly competitive with SAEs on major benchmarks, but at a fraction of the cost. So welcome to AI Paperslap.
Thanks. Yeah, it is genuinely fascinating to see a classical algorithm just jump straight into the middle of cutting-edge LLM research.
Yeah, it really is.
To really appreciate what this paper accomplishes, we have to look at the massive bottleneck you run into if you're, an ML engineer trying to interpret a model today. Like, sparse autoencoders are incredible tools.
Right.
They take the dense, unreadable activations of a language model, the so-called residual stream where all the intermediate math happens, and they map that data into a much higher dimensional space.
Which is how you find the latents, right?
Right. The goal is to find latents or features that are sparse and monosemantic, meaning each direction means one specific human understandable concept.
Yeah.
But the compute required to do this is just staggering.
Yeah, because you aren't just looking at the model. You are literally training an entirely new, massive neural network just to watch the first one.
Precisely. I mean, take GemmaScope as an example. Building that required hundreds of different SAEs, tens of millions of learned latents, and roughly 20 petabytes of saved activations.
20 petabytes. That is just absurd.
It is. Training those SAEs took over 20% of the total compute used to train GPT-3 in the first place. You simply can't spin up an SAE instantly every time a new open-weight model drops.
No, of course not.
If you just want to inspect a specific layer on a whim to see what the model is learning, the barrier to entry is completely unreasonable for most researchers.
Which brings us to the core intuition of the paper, I think. If we step back from just throwing massive compute at the problem, we have to ask what actually makes a direction in the model interpretable in the first place.
Right, and it all comes down to selectivity.
Exactly. An interpretable direction only lights up for specific tokens or, specific concepts. So if you're listening to this, imagine tracking a single concept, like the concept of dogs, across millions of random Wikipedia tokens.
It's going to be zero almost everywhere.
Right. Statistically, a direction that tracks dogs is going to sit at zero almost all the time. But when the word golden retriever appears, it suddenly spikes. So mathematically, a distribution with a massive peak at zero and long, heavy tails is distinctly non-Gaussian.
Yeah, and that statistical footprint is the key. SAEs actually learn this non-Gaussian structure implicitly.
They do it the hard way.
They really do. They achieve it through this massive, expensive, sparse reconstruction training where they penalize the model for having too many features active at once.
So let's make this visual for a second. Using an SAE is literally like searching for a needle in a haystack by picking up and individually sorting every single piece of hay until you find the metal.
That sounds exhausting.
Right. You're training a system to manually reconstruct the entire haystack just to isolate the sharp pieces. ICA, on the other hand, is a classical math algorithm specifically designed to find non-Gaussian directions directly.
So no sorting the hay?
Nope. Instead of sorting the hay, ICA is like just running a giant magnet over the pile to pull the needles out.
That is a highly accurate way to frame it, actually. FastICA, the specific algorithm they use, literally rotates the data space to maximize non-Gaussianity.
And it does that by whitening the data first, right?
Yeah, first it whitens the data. Whitening basically means stripping away the obvious basic correlations so every feature starts on a totally equal playing field.
Okay, makes sense.
Then it uses a fixed-point mathematical algorithm to find directions that are as statistically exceptional or spiky as possible.
Okay, I want to stick with the visual of rotating the data space because that can sound a bit abstract. Imagine you are looking at a messy, blob-like shadow of a complex 3D object on the wall. ICA essentially rotates that object systematically until the shadow suddenly reveals a sharp, recognizable silhouette. It mathematically twists the data until the spiky non-Gaussian features line up perfectly.
Exactly.
But if it's just rotating the data using a solved equation from 1999, why did we need things like GemmaScope? Like, why hasn't the mechanistic interpretability community been using ICA as the default starting point from day one?
Because standard, off-the-shelf FastICA completely breaks down when you apply it to modern language models.
Oh, really?
Yeah, it is incredibly brittle in these high-dimensional spaces. The activations inside a modern LLM have massive outlier tokens. You have things called attention sinks.
Right, usually like the first token or punctuation.
Exactly. The model uses those to dump excess attention scores. And these create massive spikes in the vector magnitudes. If you just run the standard FastICA algorithm on that environment, it completely fails to converge.
It just crashes.
Basically, get derailed by these massive outliers, and will often just reject an entire layer's fit, returning absolutely nothing.
Wow, so the math is sound, but the environment of an LLM is just way too chaotic.
Precisely.
And this is where the authors had to build the ICALens workflow. They put together 3 specific recipes to fix this brittleness and actually force it to work on modern GPUs. So let's dig into how they actually tame those massive outliers. The first step is row normalization.
Yes, row normalization tackles the geometry of the input directly. Before doing any whitening or rotating, they take every single activation vector and divide it by its L2 norm.
Okay, so squashing the lengths.
Right. In spatial terms, they're essentially projecting all the activations onto the surface of a hypersphere. This completely normalizes the lengths of the vectors, which completely tames those massive magnitude outliers caused by the attention sinks.
Okay, wait, hold on. I really have to push back on this stuff.
Okay, go for it.
If you row normalize the activations, aren't you destroying crucial raw magnitude information? Like, the residual stream of an LLM heavily relies on the magnitude, the sheer length of those vectors, to determine how much influence a specific token has on the next layer.
That's a fair point.
Right. If you squash everything to the same length, shouldn't you lose the very concepts you're trying to find?
Well, that is exactly what most ML engineers would assume. It feels like you are actively throwing away critical structural data. But the paper has a highly surprising, counterintuitive finding here.
Which is?
Normalizing the activations vastly improves the fitting stability, and it doesn't destroy the concepts at all. On GPT-2 Small, looking at 1 million activations, this simple row normalization increased the number of successfully accepted layers by 400%.
400%, just by projecting to a sphere.
Yeah, and it also massively reduced the total number of algorithm iterations required.
Okay, so it appeases the optimizer and makes the math stable. But do the features still mean anything?
They absolutely do. The downstream evaluations prove that these normalized components still perfectly capture the needed conceptual features.
How is that possible if the magnitude is gone?
Because the statistical footprint of a concept, whether it's the idea of dogs or geopolitics, remains fully intact purely in the angular direction of the vector. Even when you discard the length, the angle pointing to that concept is totally preserved.
That is wild. It implies the model encodes the what in the angle and the how much in the magnitude.
Exactly.
Okay, so you tame the massive outliers, but you are still operating in a 2,000 or 4,000 dimensional space. What happens when the algorithm is still struggling to settle down?
Well, that brings us to their second recipe, which is robust convergence acceptance. They call it the P95 limb rule.
Oh, right, because standard FastICA is way too strict.
Yeah, standard FastICA uses a punishingly strict stopping rule. It measures the change in all components between iterations, which is known as the limit statistic. It will only accept a fit if every single component has stopped changing and stabilized below a certain threshold.
But think about the scale of an LLM layer.
Exactly. You might have 1,990 perfectly stable, beautifully interpretable feature directions, and just 10 noisy components that keep oscillating.
And the standard algorithm just throws the whole thing out.
Yep. The standard 1990s algorithm throws out the entire layer, all 2,000 components, just because of those 10 holdouts.
That is infuriatingly rigid. I'd be so mad.
It is. So the authors introduced the P95 fallback rule. It dictates that if the strict rule fails, but 95% of the components have stabilized, you just accept the fit.
That makes so much more sense.
Right, you keep the 95% of great features and simply flag the remaining 5% as unstable, so researchers know to just ignore them.
It's such a practical engineering fix. But what if a layer is so chaotic that even the 95% rule fails?
Then they use their third recipe, adaptive refitting. It just automatically lowers the target component count for difficult layers.
Oh, nice.
Yeah, if the algorithm fails at the full hidden dimension of, say, 4,000, the pipeline automatically drops the target to 2,000 and tries again. It ensures you get the highest resolution possible without needing a human to sit there manually tweaking hyperparameters all day.
So by combining these 3 steps, we now have a stable, highly efficient algorithm. But this leads to the next crucial question in the paper. We know the math works now, but what does ICA actually recover? Are these non-Gaussian directions actually meaningful to human beings?
Right, because if they're gibberish, what's the point? To mathematically prove they are finding selective features, the authors measure something called excess kurtosis.
And if you aren't deep into statistics, a standard boring bell curve, a normal Gaussian distribution, has an excess kurtosis of 0. Higher numbers mean the distribution has heavier tails and sharper peaks. It's more selective.
Exactly. And the paper shows that ICA components are vastly more non-Gaussian than random projections. But here's the crazy part. They are also significantly more non-Gaussian than public SAE decoder directions.
Wait, really? More than SAEs?
Yeah. Which proves ICA is behaving exactly as it was designed to. But high kurtosis is just a mathematical property. It tells you the feature is spiky, but it doesn't tell you what the model is looking at in the text to cause that spike.
Right, you need to link it back to the text.
So to figure that out, the authors introduce a metric called Effective Receptive Field, or ERF. ERF measures how much prior text context is actually needed to trigger a specific component.
Let's break that down for the listener. If you have an ICA component that fires every single time the word cat appears, no matter what the surrounding sentence is, its ERF is basically 1 token.
Right, it's highly local.
But if a component only fires when a text is discussing a complex topic, like, say, diplomatic negotiations between 2 countries, it might need 10 or 20 tokens of prior context to build up that concept before it activates.
Exactly. And by measuring this ERF across different layers of the model, the authors found a really clear layer-wise evolution.
Oh, like changing as you go deeper.
Yeah. The early layers of the model are almost entirely dominated by local single-token features with very low ERFs. But as you move deeper into the model, the components rely on much broader context. They transition to high ERFs.
Which totally makes sense when you think about how a language model functions. Early on, it has to parse basic syntax and vocabulary.
Yeah.
Deeper down, it's building complex semantic reasoning.
Yep. And here is where the authors make a brilliant connection that actually solves an ongoing mystery in the interpretability field. They found that high kurtosis, that extreme statistical peakiness, correlates perfectly with low ERF.
Oh, wow. This is a huge insight.
It really is. In prior SAE research, people constantly noticed that features with high kurtosis always scored better on automated interpretability tests. Automated judges, usually other LLMs, would rate them as highly interpretable.
But no one really knew why spiky features were easier to understand.
Exactly. But the ERF metric completely explains it.
Right. Because high kurtosis features are simply local features. They trigger on short, highly specific patterns like a specific word or a grammatical prefix.
Yes, and because they are so localized, their entire activation condition is completely visible within a really short context window.
That makes them incredibly easy for a human or an automated LLM judge to look at and instantly summarize.
Conversely, features with broader, long-range context have softer distributions. They have lower kurtosis. They activate gently over a whole paragraph of geopolitical discussion.
Which is super hard to summarize just from looking at a few top tokens.
Right, which is why they score lower on automated interpretability tests, even though they are arguably the most important reasoning features in the model.
That is fascinating. So what does this actually look like when we map it to raw text? The paper does this phenomenal human inspection case study on the Polysemy word bank.
Oh, I love this part.
Me too. They feed the model a paragraph that contains the word bank used as a financial institution and the word bank used as the edge of a river.
Yeah, this Polysemy test really showcases the power of tracking ICA components layer by layer. If we look at the very first step, the embedding layer, before any self-attention has happened to combine words together, ICA shows that all occurrences of the word bank are absolutely identical.
Just the same exact feature firing?
Yes. The components triggering at that stage are labeled things like a room or place, money, and literally the letter B. The model is just looking at the raw lexical surface form.
But as you trace that exact same token through the residual stream, moving deeper into the model's layers, the context starts to separate them.
Right.
For the financial bank, you see ICA components suddenly light up for organization, dollar, and investment. But for the riverbank, it shifts entirely, triggering components representing water, body movement, and place name.
And this brings us to one of the most revealing moments in the entire paper. We call it the autoregressive trap.
Oh, yes. Explain this. It's so good.
Imagine you were reading a paragraph heavily focused on finance. It describes counters, accounts, and vaults. But then the very next phrase is about a bank of earth holding the river. When you read the whole sentence, you know instantly it's a riverbank.
But at the exact split second the model processes the token bank, the ICA components reveal what the model is actually thinking before it sees the rest of the sentence.
Exactly. ICA shows the model is heavily firing financial components. It perfectly visualizes how the model is fooled by its own left-to-right autoregressive nature.
Because it hasn't seen the word river yet.
Right, so based entirely on the leftward context of vaults and accounts, it assumes it's still in finance world.
It's a beautiful confirmation of how causal language models physically build representations in real time.
It really is.
And while we are talking about lexical structure, it's worth noting how the early embedding layer ICA handles classic word analogies, like the relationship between king and queen or man and woman.
Oh yeah, that's really clean.
Yeah, the ICA cleanly decomposes these word embeddings into shared interpretable vectors, like finding a core vector for royal or parent, and then isolating distinguishing vectors like female or morphological form. It mathematically finds the structural axes of human language without any contextual processing at all.
Okay, so ICA gives us these incredibly readable, interpretable directions. It lets us literally watch the model think. But does this actually work for controlling and probing models in practice?
Well, the authors put ICALens to the ultimate test using SABench, which is the standard suite for evaluating how useful these feature dictionaries actually are.
Right, and they start with sparse probing. This tests whether you can use these extracted features to accurately predict concepts, like classifying whether a news article is about sports or politics.
And the results are stunning. ICA is highly competitive with massive, publicly trained SAE dictionaries. It consistently beats alternative lightweight methods like PCA, ITDA, and even Matryoshka SAEs.
Which is saying something, because Matryoshka SAEs are specifically designed to have smaller, more efficient dictionary sizes.
Exactly.
Beating PCA tells us something fundamental about machine learning, honestly. PCA just finds the directions of maximum variance in the data. But non-Gaussianity, which ICA optimizes for, is a much more informative signal for concept discovery than simple variance.
Yeah, ICA finds the directions of maximum statistical exceptionality.
Which happens to align much more closely with how humans categorize concepts.
Then they measure intervention using a metric called targeted probe perturbation, or TPP. This is the crucial test where you ablate or zero out a feature to see if you can selectively change the model's behavior.
Right, like if I want the model to stop talking about a specific concept, can I just turn off the ICA feature for it without ruining the model's ability to speak English?
Yes, and at small to medium intervention budgets, ICA actually outperforms public SAEs.
That is a critical finding for anyone doing model alignment. If you ablate just a few top-ranked ICA features, the intended effect on the model's behavior spikes very quickly, while the unintended side effects stay incredibly low.
Which is the dream, really.
It is. With an SAE, because the dictionary is so massively overcomplete, sometimes expanding 4,000 dimensions into 100,000, the features are highly granular. A single human concept might be smeared across 50 different microlatents.
Let's unify our analogies here, actually. If an SAE is a massive, high-powered electron microscope that takes millions of dollars to run, but lets you see individual atoms of a concept, ICA is the trusty magnifying glass you carry in your pocket.
I like that.
It's cheap, it's instant, and if you want to make a highly targeted edit to a model's broader behavior, you don't need the electron microscope. You don't need to boot up a hospital-sized dictionary and search through 65,000 features. You can just look at the top few ICA components through your magnifying glass and get the job done.
Which brings us to the ultimate conclusion of the paper regarding the relationship between ICA and SAEs. The authors are very clear here. ICA is not a replacement for SAEs.
Right, they are fundamentally complementary.
Exactly. SAEs give you that high-resolution, overcomplete dictionary. They're necessary to find the incredibly rare, highly specific microfeatures that might only occur once in a million tokens.
But ICA gives you a compact, computationally cheap first lens. You get a dense but highly interpretable basis that fits entirely inside the standard hidden dimension of the model.
Yep, and their token-wise behavior is actually quite different when you put them side by side on the exact same text.
How so?
Well, if you look at SAE features, they look like sharp, localized spikes. An SAE feature might fire specifically on the word deposit and nowhere else. But the ICA feature activates across broader contextual spans. It will stay elevated across the whole phrase, remaining active through deposit, check, withdraw, and cache.
So it acts more like a continuous state tracker for the concept, whereas the SAE acts like a discrete impulse detector.
Exactly. Both are useful, but they offer completely different geometric views of the exact same semantic space.
And having those different views is vital. The authors actually use this relationship to audit existing SAE labels.
Oh, this is such a cool detail.
Yeah, they cross-referenced ICA components with their nearest SAE neighbors. In one case, a public SAE label on Neuronpedia described a feature as tracking math and code. But when the authors looked at its ICA twin, they realized the feature wasn't about code at all.
Oh, wow. What was it actually doing?
It was actually tracking conditional repetition across all kinds of topics. So the ICA lens helped correct the public hypothesis of what the SAE was actually doing.
That's amazing. It's a great reminder that automated interpretability labels are just hypotheses. They aren't ground truth. Having multiple mathematical lenses to view the same activation space gives us a much better shot at actually understanding what these black boxes are really learning.
It really is a triumph of classical statistics applied to modern deep learning. By just shifting our perspective away from expensive, sparse reconstruction and focusing purely on non-Gaussianity, we unlock a powerful, lightweight tool that was basically hiding in plain sight for decades.
Yeah, it's brilliant work.
So, next time you are poking around in new open-weight LLMs internals, maybe don't immediately burn thousands of GPU hours training a massive sparse autoencoder.
Good advice.
Just normalize your activations, tame those attention sinks, and run a FastICA pipeline using ICALens. It is essentially free, and as this paper proves, it exposes an incredible amount of rich, interpretable structure.
Absolutely.
It definitely leaves you wondering, though. If a classical mathematical algorithm from the 1990s can extract this much interpretable structure out of a modern LLM, basically for free, what other solved statistical tools are ML engineers completely ignoring in their rush to just train bigger and bigger neural networks to solve every single problem?
That's a great question to end on.
Thank you for joining this discussion on AI Paper Slut.